Welcome to Science Unplugged, the podcast where science and conversation collide. Join us for a deeper look into the world of innovation. We are your hosts, Taslima Farouk.
And Charvi Trivedi. Let's explore the world of science from the lab to the field. We'll dive into the stories and experiences of researchers, experts, and innovators who are shaping the understanding of our world.
Our guest for today is Dr. Shashank Gupta, who has an integrated PhD in theoretical physics. He was a postdoctoral researcher at the Applied Cryptography Unit at OIST, Japan, and is currently working as a research lead at KNU Labs. His research interests include quantum physics. Welcome, sir.
Welcome, sir.
Thank you. Thank you so much.
Sir, you are our first guest on the podcast with a background in quantum physics, and
Yep.
we are very excited to talk with you, and we are also very intrigued, but we are kind of lost at the basics of it. So, can you start by explaining what quantum physics is in simple terms for us and our audience?
Yeah, so quantum physics in basic terms itself is quite challenging. But I would like to start from the wording itself. So, quantum we know stands for discrete, and physics is a kind of understanding of how those discrete systems behave. So, the idea is to understand uh, how microscopic particles, ranging from, say, photons to electrons, what is the governing principle of them. And it is quite counterintuitive. Whatever we explore in our day-to-day activity, the size of those system is quite different than the quantum particles, and so is their physics. So people have been trying to understand the physics of those system starting from the last century, because there were quite different phenomena like photoelectric effect, black body radiation, which cannot be explained by our understanding of day-to-day systems. So it is a physics of understanding of microscopic system, to be precise.
So your words remind me of my 12th grade all of a sudden, where we were studying physics, chemistry, and everything. Nostalgia.
Yep. Yeah.
So,
And
when did you pick up
yeah.
this, sir?
Hmm.
Like, specifically, when did you get into quantum physics? Is that
Yeah.
something that has always interested you? Like Chavi said, did it start from high school or did you get into it by bachelor's?
So okay. Speaking of nostalgia, so this takes me to my undergrad. We used to have our laboratory in a dark room, and there we were performing this double slit experiment. So the I mean, so expected outcome using the classical light is, all of us know, right? It will be an interference pattern, and when you perform it with respect to, say, uh, a kind of particle which are classical in nature, the behavior is just additive. It is not, I mean, interference effect will be lost. And when you perform it with respect to, say, the laser light, and you attenuate it, continuously attenuate it up to single photon level, you will understand that right now the photons are going in a discrete chunk, but still you will have interference pattern. So what a beautiful experiment. And then I was kind of just exploring its interpretation, various interpretation, and it takes me back to the book that I read that time by Richard Feynman. And all of that explanation were seems to be okay. So this part is correct in this explanation. This part is correct in this explanation, and combined together, we are not understanding the complete picture. So that was the idea. Just keep exploring. So that was the story behind why I continued exploring quantum physics till date. So double slit experiment to begin with, and just trying to understand various explanation of it.
Hear something about something fascinating from your research journey, perhaps an unusual observation or a discovery which you felt would be like a stepping stone
Mhm.
or something like which is very you found very awestruck about.
So in theory, there are a lot of I would say there are a lot of calculations which can give rise to lot of say experimental insights. But keeping, say, audience in mind, I would just share the concept of quantum entanglement, which you can observe in, say, laboratory, and which is pretty much connected to what we are currently doing at Juno Labs. So quantum entanglement is a very fascinating concept in quantum physics. And speaking of Albert Einstein, he said that it is a spooky action at a distance, because quantum entanglement, say, exists between two or more quantum subsystem. So consider two photons which are entangled, and they could be very far apart. So one could be, say, in Delhi, another could be in Mumbai. And if you perform some measurement on one particle, it will affect the outcome that you expect at the other particle. So they are correlated. So suppose you measured the polarization of one photon in some direction at Delhi, the outcome that you expect at Mumbai will be deterministic. So this is very interesting, that how these two separated particles are connected in, say, undefined manner. What is the connection between the two particles, although they are separated, which is giving rise to correlated outcome. So that is very fascinating to create and to observe. And then there are a lot of, say, approaches to preserve such a behavior, because due to decoherence or the noise in the system, this behavior will kind of decay. But there are several approaches to preserve them, and my say PhD work is more or less related to preservation of such kind of correlation in a noise environment. Quantum entanglement can be used for several kind of purposes, ranging from quantum communication, cryptography to sensing. So just to share one basic thing which you can do for using quantum entanglement is quantum key distribution, where you need not to trust the boxes. So basically, consider two particles which are separated, are kind of measured in a defined manner, and the outcome that you will get after performing those measurements, that can form the secret keys, the symmetric keys between the two parties. Those symmetric keys then can be used for encrypted communication, and that communication will be secured by the laws of physics. It won't be secured by, say, some mathematical conjectures. So that is very interesting. In fact, the first protocol was given by Professor Eckert, who was there at OIST in Japan also. So I get to see him a lot while I was there at OIST, and he was the first one to propose this Eckert protocol for quantum key distribution using entanglement.
I have a stupid question too.
So as I said, there are no stupid questions.
Go ahead. So you just sound a bit like Sheldon Cooper from Big Bang Theory right now.
Yeah, go ahead.
Okay, so is there any connection between quantum physics and nanotechnology? Like any connection at all?
So, okay. So I did somewhat work in, say, not specifically on nanotechnology, but my understanding says that as you go in the nano dimension, the surface to volume ratio is kind of different, and that's where the advantage lies, right? So, okay, so there are several quantum effects that you can create as you go in the nano dimension. So those kind of effects you won't be having in the coarse particle. So there's a entirely different field of quantum sensing, where people try to create, say, quantum materials and other kind of like exotic drugs or exotic materials with a very dedicated, say, target or objectives in mind. So there is a connection between, say, quantum material which are generated in nano dimensions.